Hello everyone. Today we're going to be talking about the Perron-Frobenius operator. And what this operator describes is the time evolution of densities in phase space. And so usually on a computer, for a given map F, we like to start with a single initial condition x naught and see how and observe the time evolution of the trajectory from x naught to x1 to x2 and so on and so forth. We also like to consider a large ensemble of initial values x naught that are described by the probability distribution rho naught of x, and how this probability distribution evolves in time. And so after n iteration steps later, it becomes rho n of x. Now, of course, we can take a large number of values where that number is s, and that is the set of initial values, or the x naughts, and iterate each of those n times. And but we can't precisely observe the function rho n of x. What we can observe, though, is the number s sub a, where s sub a is defined as the number of iterates x sub n found in a certain part of phase space. Let's call that part of phase space A. Now, to more clearly define what our probability distribution is, we can talk about the relative frequency of iterates x sub n in subset A, and that is described by the following expression, where the number of iterates in A divided by the total number of values is equal to the integral over A dx of rho n of x. So this gives us a clear idea of what distribution exactly we're talking about. But the main topic of the video today is the Perron-Frobenius operator, and so let's define that. So the Perron-Frobenius operator is defined with the following expression: rho sub n plus 1 is equal to L of rho, or operating on rho sub n, meaning that the operator is acting on the distribution after n iterations, and that is equal to the distribution of n plus 1 iterations. And this operator, again, determines the time evolution of the density rho sub n. So often when we talk about probabilities, we care about the conservation of probability. So let's write down our statement in this notation for the conservation of probability. So the conservation of probability is as follows. The integral over the set A of dx rho sub n plus 1 of x is equal to the integral over A prime. Talk about what A prime is here in a second, of dx rho n of x. And so the left-hand side is the integral over the set A, and the right hand is the integral over the set A prime, where A prime is defined as the inverse function of A, or inverse map, where our given map is F. And so to state this in a different way, all of the points in A prime are mapped onto A after one iteration steps. Or to use the terminology of the field, A prime is the pre-image of A. And so taking this expression for the conservation probability and denoting this equation, or this expression, as equation 1, because we will be referencing it a little later, we can rewrite equation 1 here if we restrict ourselves to one-dimensional maps, later we will extend the final result of the final result to higher dimensions. And the goal here is we're trying to find a more explicit expression for the Perron-Frobenius operator, because this equation here at the top gives us a definition, but it doesn't give us a very explicit expression for the operator. And so that's what we're going after now. And so again, restricting ourselves, as I mentioned before, we're going to restrict ourselves to one dimension. And so taking equation 1, we can rewrite it as the integral from u to w, where a is defined as the interval from u to w, dx rho n plus 1 of x is equal to the sum over sigma of the absolute value integral chi sub sigma of u, the upper bound is chi sub sigma of w, dx rho n of x. And so here there's a couple things that we need to define. We already talked about u and w, but sigma and chi sub sigma we have not defined yet. And so chi sub sigma is defined as the inverse map sub sigma of y, or in other words, the preimage of y under F. And for many maps, there isn't a single preimage. Let's say that we have a piecewise function. There would be multiple inverse functions or multiple preimages. Or for the logistic map, for example, there are two preimages because there's a positive and negative root solution to the equation. And so sigma is the subscript that helps us distinguish, or that distinguishes between the various preimages of y. Now we are going to do a substitution in order to write this expression, or this equation 2 in other terms that will help us to get to the final result that we're going after, which is again the explicit expression for the Perron-Frobenius operator. And so we will make the substitution x to chi sub sigma of y, and make that substitution in equation 2. And the result of that is, just repeating the left-hand side, the integral dx rho n plus 1 of x is equal to, and again, this is still the sum over sigma, and we're integrating from u to w after this substitution over dy, and the integrand is rho sub n of chi sub sigma of y, and this is over the derivative of chi sub sigma of y. Now this equation is valid, or has to be valid, for arbitrary values of u and w. Thus, the densities rho sub n plus 1 and rho sub n must satisfy the following expression, where rho sub n plus 1 of y is equal to the sum of rho sub n of chi sigma of y all over the absolute value of the derivative of chi sub sigma of y. Now, the left-hand side of this equation may look familiar. We can actually rewrite that in terms of the operator based on the definition that we gave at the beginning for our operator, where rho sub n plus 1 is equal to the operator L acting on rho sub n of y. We'll drop the subscript n since it will also be found on the right-hand side of the equation. And thus we don't need to differentiate between the two probability distributions. So again, rewriting the right-hand side. We now have an explicit expression for the Perron-Frobenius operator. Often, the right-hand side of this equation is written in a more compact notation that many find more useful. And so let's go ahead and rewrite that, where x is for all the inverses, or essentially all the preimages, a row of x, sum of a row of x divided by the derivative of the map. Now this is our final solution. This is the explicit expression for the Perron-Frobenius operator that we were looking for. And in order to extend this to higher dimensions, we need to make one simple substitution, and that is in this expression underlined in green. We would need to substitute the derivative of the map with the Jacobi determinant of f of x. And that would be the final solution for higher dimensions. Now, the fixed points of the linear operator L are quite important, and these fixed points are different than the fixed points of the map itself in phase space. These fixed points are in the function space, and they are entire fixed point functions. And they can be written as the operator acting on the probability density rho of x is equal to rho of x. And rho of x is called the invariant density, or this fixed point is called the invariant density, because when the density is acted on by the operator, it returns the density itself. And therefore, it is invariant under the dynamics and describes the stationary state of the system. So let's talk about a specific example. Let's find the Perron-Frobenius operator and the corresponding invariant density, or one of the corresponding invariant densities for the tent map example. I will make a small note that for many maps there are often multiple invariant densities, and we usually only care about the natural invariant density, but we will leave that discussion for another time, as there are some details that need to be dived into a bit deeper. So the tent map. What is the tent map? It is a very common map that is used in nonlinear dynamics and chaos because it exhibits a lot of interesting behavior while being quite simple, and is often used as a sort of test function to give a good example of different measures, and here to find our operator and the invariant density of that operator. And so the tent map is defined as f of x. It is a piecewise function where it is 2x for x is less than or equal to 1/2, and it is 2 times 1 minus x for x is less than 1/2. And this is defined in the part of phase space from 0 to 1. Now, the invariant density can actually be found through a geometrical consideration, but we'll leave that discussion for another time. Let's go ahead and find the Perron-Frobenius operator and then the invariant density from there. And so looking back at our expression for the operator, we need two things from this expression. or to find two things from the map, we need the preimages and we need the derivative of the map. And so to begin, the derivative, or the absolute value of the derivative of this map is simply 2, and the preimages are x sub 1 is equal to y over 2, and, or sorry, chi sub 1, and chi sub 2 is equal to 1 minus y over 2, where chi sub 1 corresponds to the first part of the piecewise function, and chi sub 2 corresponds to the second portion of the piecewise function. Now, plugging this into our expression for the Perron-Frobenius operator, we have the operator acting on rho of y is equal to the inverse of the derivative times the sum of the probability densities with the preimages plugged in. And so rho of y over 2 plus rho of 1 minus y over 2. And so this is our expression for the Perron-Frobenius operator. And now let's talk about the invariant density of this operator. Again, the invariant density is when the left-hand side of this expression is simply equal to rho of y. And so just rewriting what we have here on the right-hand side, 1/2 times rho of y over 2 plus rho of 1 minus y over 2. What satisfies this function is actually rho of y is equal to 1, or in other words, the uniform probability distribution. And so if we were to do this numerically, we would take a large number of initial values x naught that were described by the uniform probability distribution, and then we would iterate each of those initial values and plot that probability distribution and see if it did in fact remain the uniform probability distribution, or if it was in fact invariant. And we actually did this, and the results are here. Where on the left-hand side we have a large number of initial values that satisfied the uniform probability distribution, as can be seen here. And it was normalized, and so hence the maximum is 1, or the area under a curve here would be 1. And then we iterated each of those initial values and plotted that probability distribution as well. And we iterated 12 times, so from n equals 0 to n equals 12, and plotted that. And again, we can see that we do indeed have the uniform probability distribution. And therefore, this shows that it is indeed an invariant density of the tent map. And so in this resource listed here, there is a further discussion of this operator, and many of the materials today were utilized from this resource. Something interesting about the Perron-Frobenius operator is that there's a generalization of it, and it's called the transfer operator for a given inverse temperature. And the largest eigenvalue of this operator is related to the topological pressure. And so this generalized operator is actually a really powerful method for calculating the topological pressure. And so I would highly recommend looking at this resource and learning how that is actually done. For the sake of time, we will end things here today. Thank you so much for watching, and I hope you have a great rest of your day.